Okay, so in this video I'd like to calculate some equilibrium constants, but first I'm going to do an aside on how to estimate activities. So let's start with a gas, the activity of a gas. In particular, we're going to look at perfect gases. If we go all the way back to chapter 3E, which you can find this on page 58 of my lecture notes, we have this equation for the molar Gibbs energy of a gas at a pressure P is equal to the molar Gibbs energy for the standard state plus RT ln P over some standard pressure. Typically, we take the standard pressure to be 1 bar. And if you also recall that for a pure substance, which is the only thing we were dealing with when we first approached chemical potential, for a pure substance, the molar Gibbs energy is the chemical potential. And that started out as our definition, but then we developed a more general definition when you're not talking about a pure substance. However, in this case, we're going to use this even though the gas may not be pure. Okay, so notice I said that we're estimating activities. Okay, so this is an approximation. So if we approximate this gas as being mostly pure, close to pure, then I can make this substitution mu for Gm in this equation up here. And so I drop the P and I replace Gm with mu here, okay? So this standard chemical potential is up to us to choose. In this case, the standard pressure has already been chosen. And in this case, let's let the standard chemical potential be the chemical potential of the gas when it's pure. Then making the substitution, we have this equation, and now compare that to this equation. Which you can find on page 105 of these notes. And comparing these, you can see that they're the same. So the arguments of the natural log must be the same. And so we can conclude that A, and again, this is an approximation, A can be approximated with P over P standards. That is the partial pressure of the gas over 1 bar. Okay, now for a pure liquid or solid, we're going to return to this equation. Mu equals mu star plus RT ln A. And if this is a pure liquid or a pure solid, then that implies that mu equals mu star, which implies this quantity must be 0. So the natural log of A must be 0, which would imply that A equals 1. Okay, so for a pure liquid or solid, we can write A equals to 1. All right, and also in 5F, we talked about solvents and solutes. So we said a solvent as it approaches the ideal case, obeys Raoult's law, which is that X is approximately P over P star. And A is an approximation for X, which is an approximation for P over P star. So we're going to use this as our estimate for the activity of a solvent. And for more info, you can refer back to chapter 5A, page 85 of the notes. And then for a solute, we saw that they, in the ideal case, obey Henry's law. And Henry's law says A is equal to P over Henry's constant. And you can find that on page 107 of the notes. Or, in terms of the molality, I can also write A as gamma, which is the activity coefficient, times the molality over standard molality. I did not derive this in the notes. If you want to see this derivation of this formula, I'll refer you to page 185 of the textbook. Okay, so let me summarize all of these in a table. So for a perfect gas, we can estimate the activity as P over P standard, where P standard was 1 bar. For a pure liquid or solid, A is exactly 1. For a solvent, this is Raoult's law, A is approximately P over P star, the partial pressure over the pressure when it's pure. And for a solute, we can write A as the partial pressure over Henry's constant, or the activity coefficient times the molality over the standard molality, where the standard molality was set to be 1 mole per kilogram. Okay, let me show you an example of using these estimates. And this is an example we're going to talk about the reaction where calcium carbonate, solid, is decomposing into calcium oxide, solid, plus carbon dioxide, gas. All right, all the stoichiometric coefficients are 1. So the power of all the activities is going to be 1. So using our definition for K, we have the activity of the products on top. So I have the activity of calcium oxide times the activity of carbon dioxide divided by the activity of calcium carbonate, solid. And since this is a solid and this is a solid, we can set these equal to 1. And I'm left with just the activity of CO2 gas. And if we're treating that as a perfect gas, we can estimate that as the partial pressure of CO2 divided by 1 bar. So while we may not always know the values of these activities at some point during a reaction or during equilibrium, we can approximate them. We can estimate them in terms of quantities that would be easier to measure in a laboratory. Okay, so now finally I'm going to do an example of calculating K. So first, as a reminder, at equilibrium, we know that delta Rg equals 0, as discussed in 6A.1, and we relabel Q as K at equilibrium. And those two things together, when we use equation star from a while back earlier in this lecture, then we have 0 equals the standard Gibbs energy of the reaction plus RT ln the equilibrium constant. And so that gives me this equation. So this is the equation we're going to use to calculate K. As I mentioned earlier, this standard Gibbs energy of reaction is useful for finding K. So in this example, we're going to do the reaction nitrogen gas plus hydrogen gas is in equilibrium with ammonia gas at a temperature of 298 Kelvin. So step one is to find this Gibbs energy of reaction using the method that we've been doing, that we did much earlier in the semester. Okay, and if you need a refresher, you can look back to page 52 of these notes or section 3D in the textbook. So just as we did back then, I'm going to compute this Gibbs energy of reaction using the Gibbs energy of formation, which I can find in a table. And so I'll start with the products because they have the positive coefficients. So this is going to be 2 times the Gibbs energy of formation of NH3 gas minus 1 times the Gibbs energy of formation of N2 gas minus 3 times the Gibbs energy formation of H2 gas. And both of these happen to be 0. So I'm left with 2 times this, and we look this up in a table. We have 2 times negative 16.45 kilojoules per mole is the Gibbs energy of formation for ammonia gas. Okay, and now step 2. Now that we have a value for delta Rg standard, we're going to put that up here and we're going to use that to calculate K. So K is going to be E to the negative delta Rg standard over RT, which equals E to the negative of a negative. So I'm going to have 2 times, and I'm going to convert this to joules. So 16.45 times 10 to the 3 joules per mole over my gas constant times my temperature. And as we saw before, when we used this, all the units cancel. So I get a unitless number, which is what we expect. And then plugging all these numbers into a calculator, taking E to this exponent, I get 13.27. I'm sorry, that's the natural log. I get 5.85 times 10 to the 5th. Okay, so this is an exact value. This is not an estimation or approximation. This is the exact value of K, the equilibrium constant for this reaction. Now, another way to calculate K would be from the definition of K. So from the definition, K equals the product of the products raised to their stoichiometric coefficients. So the activities, I should say, of the products. So the activity of ammonia squared over the activity of N2 times the activity of H2 cubed. And this is also an exact value for K, or an exact way to compute K. Now, as I mentioned, we may not always know the activities, so it can be useful to use approximate values for these activities in terms of quantities that we might know. So let's try that as well. So these are all gases. So we're going to use, looking back at the table, the table where I summarized the different ways of estimating activities. For a gas, we can estimate it as P the partial pressure of the gas over 1 bar. So let's insert that formula for all of these activities here. So in the numerator, we're going to have, this is squared, the activity squared, so I'm going to have the partial pressure of NH3 over standard pressure squared. And in the denominator, I have 1 over this activity. So that's going to be the reciprocal of this fraction. So standard pressure over the partial pressure of N2. And then same thing here, reciprocal of this fraction, since it's in the denominator. I'm going to get the standard pressure over the partial pressure of H2 cubed. And we see I have a standard pressure cubed and another one, so that's 4th power in the numerator, 2nd power in the denominator. So I'm left with the 2nd power in the numerator. So I'm going to have the partial pressure of ammonia squared times the standard pressure squared over the partial pressure of N2 times the partial pressure of H2 cubed. Okay, and this is not an exact value like this one is. This is a approximate value for the equilibrium coefficient, or the equilibrium constant. Okay, so this was an example of finding K, and we did it in a few different ways. We had 2 ways where we got an exact result, and 1 way where we estimated the result in terms of partial pressures.